Graphing trigonometric functions. Do exactly what you did with your other functions. Meaning, find the x-intercept, the y-intercept, the vertical asymptote, the horizontal or other. So the function we're going to look at, y equals x minus cos x, and we'll restrict the section that we're looking at so we don't get multiple answers. So the x-intercept, we'll let y equals 0. Bring the minus cos x over. And we're trying to figure out, well, first of all, does cos x ever equal x? I'm going to draw a picture. So this is the graph of cos. This is the graph of y equals x, and they cross, which means there is a solution to this equation. It's somewhere between 0 and 1, but I don't actually know what it is. So I'm just going to say, yes, there's an x-intercept, and we'll worry about that later. The y-intercept, let x equal 0. The cosine of 0, you could do it from the graph. When x equals 0, what is your y value on the graph? I'm getting an answer of 1 for that. So 0 minus 1 gives me negative 1. For those who don't like what I just did, you could draw yourself a unit circle. We're talking about an angle of 0. So there's your angle of 0. It would end at the point 1, 0. Unit circle has a radius of 1. Cosine is x over r, and that's where that 1 comes from. So however you do it, the cosine of 0 is 1. The asymptotes, do we have a fraction? Nope. This is not a rational function. It's not a fraction. So the answer is not. It's nice and quick. Let's find critical points. So we're finding out where the slope of the tangent is equal to 0. The derivative of x is 1. The derivative of minus cos, which would be positive sign. We'll let that equal 0. Bring the 1 over. Now, where does sine x equal negative 1? Sine is y over r. So we're looking for where y equals negative 1 because our circle has r equal 1. So this is what we really want to know. Where does y equal negative 1? So 1, 0, not there. 0, 1, not there. Negative 1, 0, no, that's the x value. 0, negative 1, yes. That's where we have a y value equal to negative 1. And when you have a y value equal to negative 1, you'll have a sine value of negative 1. So what angle is that? 3 pi over 2. So now we have to figure out our plus minus chart. So we'll put 3 pi over 2 on the number line. Keep in mind, we said just start at 0 and go as far as 2 pi. So I'll put those in so we remind ourselves not to go any further. We're plugging into the derivative. The easiest way I find to think about this, the sine graph has values that go from negative 1 to 1. The only place it equals negative 1 is at 3 pi over 2. Everywhere else, it is bigger than negative 1. So when you add 1, it'll be positive. And when you add 1, it'll be positive. When it equals negative 1 and you add 1, it's 0 right here, which is why that was a critical point. So that's interesting. Plus and plus. So that means we're increasing from 0 to 3 pi over 2 and increasing from 3 pi over 2 to 2 pi. And decreasing nowhere. What is that actual critical point? We said it occurred when x was 3 pi over 2. Y is equal to x minus cos x. So we'll put 3 pi over 2 in. And at an angle of 3 pi over 2, we're calculating cosine this time. So that's x over r. We know that r is 1. And your x value there is 0. So this just becomes 0. The cosine of 3 pi over 2 is 0. That leaves us with 3 pi over 2. What a delightful looking critical point that is. So we're expecting the slope of the tangent to equal 0 there. And it's increasing and increasing. Huh. So it must be doing something like this, increasing, flattening out, and increasing again. So it is a critical point because the slope of the tangent is 0, but it's not going to be a max or a min. The second derivative. Derivative of 1 is 0. Derivative of sine is cos. Let that equal 0. Where does cos x equal 0? cosine is x over r. With the unit circle, r is always equal to 1. If we want to get an answer of 0, we're looking for where does x equal 0. Not there, because x equals 1. 0, 1, definitely there. So one possible answer is pi over 2. Negative 1, 0, no. And 0, negative 1. That's another place that we could have x equals 0. So our answer pi over 2 and 3 pi over 2. All right, let's draw our plus minus chart. Pi over 2 and 3 pi over 2. Again, hold off and only go from 0 to 2 pi. We're looking at the second derivative, which is cosine x. So let's think about this. You familiar with the CAST rule? Between 0 and pi over 2, all your trigonometric functions are positive. So cosine is positive. Between pi over 2 and 3 pi over 2, cosine is negative in those two quadrants. Between 3 pi over 2 and 2 pi, that's where cosine is positive. So all I did is look at the CAST rule and determine where cosine is positive and negative. Positive in the first quadrant, negative in quadrant 2 and 3, positive in the fourth quadrant. So we have concave up between 0 and pi over 2 and 3 pi over 2 and 2 pi. Concave down between pi over 2 and 3 pi over 2. 2 points of inflection. First one when x equals pi over 2. If pi over 2 minus the cosine of pi over 2. So we're going up to this point. That's where the angle of pi over 2 takes us. Our x is 0 and our y is 1. Cosine is x over r. So again, that is just 0. So pi over 2. So our point, pi over 2 and pi over 2. The second one was 3 pi over 2. Now we've done this one before. This was our critical point. Cosine of 3 pi over 2 took us to here. Cosine is x over r. So this worked out to be 0, and y equals 3 pi over 2. So we have 2 points of inflection. Lovely and symmetric those. And here's all the information we found out. So let's draw it. There's an x-intercept somewhere between 0 and 1. We don't know where. We'll worry about it later. There's a y-intercept of negative 1. And because of these points, pi over 2, pi over 2, I put my axis in terms of radius. 3 pi over 2, 3 pi over 2, because it's super easy to find those. But it's a little tricky to find that. So pi 3.14, estimate is about 3. So minus 3 over 4 is not quite to minus 1. Estimate about 3, that's negative 1.5, so somewhere around here. All right, we'll use increasing and decreasing to check our function. And I have to connect the dots concave up from 0 to pi over 2. So I'm going to be concave up in here. Concave up from 3 pi over 2 to 2 pi. Always increasing? All right, so it's going to be always increasing. So let's do something like this. In between these 2 points, concave down. So our graph looks something like that. Goes concave up, concave down, concave up. This was a critical point. So the slope of the tangent should actually be 0 at that point. So that looks a little better than my graph. So there's our concave up, concave down, concave up. Now back to this one. We can double check with the increasing. We're always increasing. So that's how we knew we had to keep rising, and keep rising. So again, there's the pretty looking graph. And your job, stay on the page you've been working on, but time to do some trig graphs. So again, it's really just the same thing you've been doing all along. Have fun.